So we're going to go ahead and do a quick video here on vectors and pretty much everything that we need to know about them for this general physics level. This doesn't necessarily apply to higher level type mathematics where you start to learn that vectors are a different thing, but we need to start differentiating a different type of number. And so the main idea here is vectors. Now, the numbers you're probably mostly used to are called scalars, okay? And these scalar numbers, they do exactly what they say. They simply scale other numbers. These are like your coefficients out in front of your equations and stuff like that. But they basically they basically have a size, a magnitude. Think absolute value, a magnitude, um, but they don't have a direction. But no direction. All they do is just tell you how big something is. Uh, some examples of this could be like the speed of your car. If you look at the speedometer on your car, your speed. Something else could be mass. You have 25 kilograms of something. There's no direction to these things. They're just full numbers. One that kind of changes in the future, but for our level, we still count as a scalar is time. You know, 36 seconds and stuff like that. Later on, that doesn't quite stay that way. It becomes a part of a vector, not really a vector into itself, but part of one. And then we have something a little different. We have vectors. And as far as we're concerned, we're going to treat vectors essentially as a number, a quantity that has magnitude, just like a scalar does, magnitude with a direction. So this could be something along the lines of just having speed and your direction. So you're in your car, you're driving, you look at your speedometer, it reads 15 miles per hour. If you just read that number, that's just a scalar. But if you combine that, if you take the speed of your car and then you also grab a compass and it tells you, you look at the speed and you're going 15 miles per hour and you look at the compass and you're going exactly due north, then you have a 15 miles per hour north, and now you have a direction with it, right? So that becomes then a vector, and we actually give it a slightly different name. We call it velocity, where you have a direction attached to your speed. If I just told you I was going 60 miles an hour, and even if I told you where I started from, you wouldn't know where I ended up. I could have gone 60 miles an hour in a big circle. I could have gone in one direction. I could have gone in a zigzag. I could have just, you know, done any number of things. But here, I'm telling you that I went, I'd say something like I went 60 miles an hour north. Well, if you know how long I went north, you know exactly where I'm going. You know the line I'm going on, and you know that I ended up straight north of where I was. Okay, so velocity is one. Weight is another example of a scalar. It actually has a direction. It's a force. It is pointed downward. Your weight pulls you down to the ground. So that is another one we would learn would be acceleration. Acceleration has a direction. You can be accelerating north, south, east, west, up, down. There's a direction for these things. And so we can think of these basically as arrows. If I draw an arrow, I can have an arrow and it has a length to it. That would be the magnitude. And it has the direction that it's pointed, so it has a direction. And I could have a different arrow that could be shorter. It has a smaller magnitude and a different direction than the previous one. And so it's a good idea to think of vectors as arrows, even though acceleration isn't necessarily an arrow, but it's a good idea to kind of think of it. Up here for scalar, we also could have had distance. Like I walked 5 miles. Well, did you walk 5 miles in a big circle? Did you go on a treadmill and just stay in one place, or did you walk in a straight line? If we add a direction to it and keep that direction, and I'll write it off here to the side. If we keep that direction, then it becomes not distance, uh, not distance, but displacement. Sorry, I don't know why I forgot that word there for a second. Displacement. Okay, and this one would have a direction associated it. So I could say, oh, all right, I ran 20 miles. Well, I have no idea where you ended up. I just know it's within 20 miles of where you started. Here I said, I ran 20 miles northeast. Well, I know I went 20 miles northeast, and I know exactly where you ended up. It's displacement. And displacement, it matters. So you could have a distance of 20 miles that you walked and have a displacement of 0 if you walked around in a big giant circle. So this displacement has to do with where you started to where you ended. This is just how many steps you basically took. All right, so we'll talk more about the difference between those when we actually get into doing that kind of stuff. But just for now, this is just some examples of different scalars and vectors and what the difference is between these two very important ideas, scalar, vector. Scales things, has a magnitude and a direction, not just a magnitude up here. One of the big things we can do with these vectors is we can add them. Now, if you're adding scalars, it's really easy. 7 grams plus 3 grams is 10 grams. But if you're adding vectors, that's not necessarily the case. So if I have something like 7 meters, thinking in displacement with a direction to it, plus 3 meters, my total displacement does not necessarily, so not necessarily, well, that just means not. It might equal 10. It might equal 10, but it doesn't necessarily have to actually equal a displacement of 10. And so if you want to think about this, we can just draw this out. Let's say I walked 7 meters this way, 7 meters, and then I turned and I walked 3 meters this way. I know I didn't get those exactly to scale. My 7-meter one should be longer. Should try and make these to scale. And I look at this and I say, all right, well, what's my displacement? Well, displacement is straight from where you started, your start, to where you end. And if I look at these two vectors and I add them up like this, well, right where I started to where I ended, this essentially makes a triangle here. And this vector that I drew in here, this other arrow, is what is known as the resultant. All right, resultant. It's when you add two vectors together. And if I look at this, this is not 10. This is not 10 because this hypotenuse is definitely not 10. Even if this is at a right angle here, then we could do Pythagorean theorem and do 7 squared plus 3 squared. Right? So 7 squared is 49 plus 3 squared is 9, and take the square root of that, and we're basically taking the square root of a number that's right near 60, and I want to get you an exact number here, so I grab my calculator, and so I've got 49 plus 9, that gives us our 58, and then when we square root it, we've got 7.6, maybe a 2 we could add on the end because it would round up to 7.61577 on my calculator. But this would be then that many meters. That's how far away you would be in a straight line from where you started. It would definitely not be 10 meters away. The only way it would be 10 meters away is if this 3 meters had been in a straight line continuing on the end of that 7 meters. Like if it had come out this way and been the 3 meters here, then we'd be 10 meters away from where we started, and it would look like it added like the scalar, but it didn't. So if we look at this path, we walked a total distance, like if we walked this, we walked a total distance of 10 meters, but our actual displacement, the vector resultant, the addition of these two vectors, is not 10 meters, it is less than 10 meters. 10 meters is more like the maximum it could be. And we could have even walked 7 meters this way and 3 meters back this way, in which case we would have been 4 meters away from where we started, and that would be the resultant. It's basically a vector that represents the sum. It's a vector sum of other vectors, 2 or more other vectors, okay? And then we call that our resultant. Okay, so that's That's a pretty important thing. And there's a few ways we can do this. We can do this like I did just right here. If it's a right triangle, we can do Pythagorean theorem and we can get it. Or you can do it even graphically. You could grab out a ruler and measure out. You don't even have to do it to scale. You could, instead of doing 7 meters, you could do 7 centimeters across. And then you could do 3 centimeters up. And then you could just grab out your ruler and measure how far the two ends are apart. If you were sure you used a protractor and all that kind of stuff and made sure all this was really nice and neat, and you could see how many centimeters this was here and just, scale that up to meters, and you'd say that's how far you went. So you could do this graphically as well as just doing it mathematically like I did there. And we'll get some practice done on doing it graphically later. There are some properties that go along with these vectors. Properties. Some of the things you can do with them, like for example, you can move vectors around. You can move them as long you can move them really anywhere. Move them anywhere as long as you don't stretch them. In other words, or compress them. If you don't stretch them or compress them, you don't change their length, you don't stretch them or rotate them. So I could have a vector, say, that was right here, and I could take that vector and I could just grab a hold of it. This is the tail end of it. I could grab that tail. We call this the tip here, the tail and tip, and I could just slide it over to here and put it right there. And it has the same length and it's at the same angle. Pretend I drew them at the exact same length and the same angle. And then these are both the same vector. So I could label this is vector A and this is vector A, and they're the same vector. If I were to take and rotate that vector, even keeping its length the same, then this is no longer the same vector. This would have to be some new other vector B. Okay, now we want to also add something on here, is that when I'm putting these variables down for these vectors, how do you know it's a variable? How do you know this variable is a vector and not just some scalar? Well, the trick to this, usually, a lot of times in your textbook, it'd be like bold, it'd be a bold letter, or if you're writing it yourself, you just put like a little arrow or a half arrow over top of it that means that's a vector. Without that there, then it looks like a scalar, and it just helps you tell the difference between what letter did you write that's a vector or as a scalar. Okay, so that's the first property. You can move them around all you want. You don't have to keep them where you started, you move them around. The second thing is when you do add them, the second property is you can add them in any order you want. Add in any order. Right? So the way you add these is you basically want to put them tail to tip. And the way I think about it is you want to use these arrows as though you're drawing out a path for someone to walk along and follow. So if I had, say, this vector, and then I went up to this vector here, and then I had another vector that went over this way, and I would just put these like this. So I'd walk along the first vector in the direction of there, and then I'd walk along the second vector, and then I'd walk along the third vector. I've basically added these up. I've put them in an order that lets me add them, and I get a resultant that looks like that. Okay, right from the start to where you ended up, and that would be that resultant we talked about a few minutes ago. And let me label these just so this makes a little. Let's call this vector A. Let's call this vector B. And let's call this vector C. Well, I added them up in this order, but it could have really been any order that we wanted. So let me try adding them in a different order. I'm going to use a different color for this. What if I started with B first? What if I walked B first? Because remember, I can move them anywhere I want. Then I walked along A, and then I did the same thing. I just did C again. A is here now, and then I did C. So instead of doing A plus B plus C, so A plus B plus C, and these are all vectors, I changed the order, and I did B plus A plus C, right? I did that, and I got this. And if you notice, I ended up at the exact same spot. I ended up right here at my end. Remember, this was my start, and I ended up at the same ending point here. So if I had walked that, I'd get to the same end place, which means that these two things, they're equivalent. They are equal to each other. A plus B plus C equals B plus A plus C. You can add them in any order, and if you try it, you could see that you could do C plus B plus A, and the order just isn't going to matter. So you can do that all you want. The next thing is, other than adding vectors, we can also subtract vectors, and you can subtract them in any order you want. Now, well, how do you go about subtracting them? Well, remember that you can subtract them. Remember that subtraction is really just addition of a negative. So if I have vector A here, let's say, I know I'm using A a lot, and then we have vector B, and I want to do A plus B, I do what I did before. I line them up in a walkable path, A, then B, and I get that resultant, A, B, and that's the thing. And I could have done B, then A, and I would end up in the same spot, and I get that resultant. This resultant here, we'll call it R, vector R, that resultant. But what if I wanted to do A minus B? What if I wanted A minus B? You know, what is that one going to be? Well, if you think about it, minus B is really, this is just A plus negative B. Just like with regular numbers, with regular old scalar numbers you're used to, it's addition of a negative. And the way you do negative B is pretty simple. It's exactly the same as B, just pointed the other way. You just put the arrow on the other end, and this is minus B. And so then I just go about adding them just like normal. Here's A, and here's minus B. So A, vector A, and minus B, and then I'll get my resultant from my starting point to my ending point. There's my resultant R, and this resultant is different than this resultant, so I'm going to call this resultant 1 and resultant 2. Use a little subscript just to differentiate them, because these two are definitely not pointed in the same direction, and they are not the same length. They're different vectors. The next and last thing we can do with vectors is we can multiply them by scalars. Okay, there are of course more rules than just here. You can actually, there are ways to multiply vectors together and stuff like that, but none of that we need to worry about right now. Those can get kind of complicated. But we can multiply by a scalar. We can multiply by a scalar. Okay, so we can multiply it by a scalar. S-C-A-L. Scalar. Okay, and that's what I told you. Scalars do that. They scale things. And what do they scale? They scale vectors. So if I have the vector, if I say I want to take some vector, let's use our friend vector A again, and I want to do 2A. All right, what's 2A? Well, if you think about it, what does multiplication tell you to do? It tells you to do repeated addition. So essentially, you're doing A plus A, and that's what you're going to get. These two guys added together in a nice walkable path. You would start here, you'd walk along A, then you'd walk along A, and you'd be done. And this would be essentially the vector. I'll draw it right next to it. This would be the vector 2A. Okay, 2 times A. It's twice as long. We have scaled it. And you can even scale it by a half. You could do 1/2 A, in which case you'd have a vector that's the same direction, same everything, just half as long. So that would be 1/2 A, something like that. Okay, so be careful about that. And then the one last little note I want to make is be sure when you're doing this that you do that walkable path, that tail to tip, they say walkable, something like that, walkable path. What I mean by that is if I have to add vectors A like this and vector B, I don't know, what did I do for B? Something like that. So vectors A and vectors B, if I have to do A plus B, I can't do something like this. I can't do B and then do A, or I'm sorry, I put that in the wrong spot. Let me grab my little eraser. Let me do that again. You can't put them this way. I put them the wrong way. You can't do B and then do A like this. Because if this is the case, you know, you have to walk in the direction of the arrows. So if I walk along A, Then I'm here, and now I can't walk along B because B is way back here. I'd have to like magically teleport back here or something to walk along it. So this is not correct. You would not do, this is not A plus B. That's not the correct way. That's wrong. You would want to do A, walk along A, get to the end of A, then do your next vector. So just be careful when you're doing these that you don't end up doing something like this. Make sure that you can go from the starting point to the ending point without ever lifting your pencil and with only following the direction the arrows are pointed. Okay? In the next video, I'll do a little bit more with this, where we're going to actually, work a little more on finding resultants.